In this section, we're going to look at proportions again, and we're going to test for the difference between two proportions. So what I want to do is let me do an example to explain sort of how this works and to remind you the basic idea of proportion. So suppose in a group of 780 people, 20% are left-handed. So how many people does that actually represent? Well, you can do it in a couple of ways. We could say the 20% is equal to a certain number of people out of 780. So if I wanted to figure out how many people that was, let me convert the 20% to 0.20 equals x over 780. And then I'll multiply both sides by 780. And then when you multiply that together, we get 1560. So we get 156 equals x. So all this is saying is that the 20% is the same as 156 over 780. And our notation that we'll use for all of these things, the 156 will be x, and the 780 will be known as n, the size of that particular thing. In particular, I'm going to actually talk about two groups. So what I'm going to do is I'm going to call this x and x1, 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 x1. x1, and in fact I'm going to call the n an n1 because now I'm going to talk about a second group. Now in a second group, that is independent from the first, so there's no relation between the first group and the second group. So in a second group independent from the first, we have 1,820 people, and 15% are left-handed. So just as before, we have 15% equals, this time since it's a different group of people, I'm going to call it x sub 2, and then I'm going to call the 1,820, I'll end up referring to that as n2. So then I'll take 0.15 equals x2 over 1820. Let me multiply by the 1820. And let's see what we get. So I get 273 equals x2. So basically we have 15% was equal to 273 out of 1820, and that is what we'll call x2 over n2. Now we want to figure out what percentage of lefties are in both of these groups combined. Now, for the combined group that consists of groups 1 and 2 above, we have an overall proportion of, well, I don't know what percent is going to be, so let's put question mark percent, but I want to know what percentage of left-handers we have in the entire group. So we had 156 lefties from the first group, and then we had 273 lefties from the second group, and that is out of a total of What was the 780 people plus 1,820 people? And if I simplify this, I get 429 out of 2,600. And then use your calculator to get this percentage. I get 0.165. So my overall percentage then is 16.5% of the combined group are left-handers. So that's basically the idea. A proportion in general, any kind of proportion takes this form. P equals X over N. X are those people with a characteristic that you're interested in, and N is the total number of people. P, of course, will be a percentage or a decimal of some kind almost always. But in any case, so X are the number of items that have a certain property that is being studied. Of course, N is the total number of items. I'm not sure what a better way to say that, but I want that kind of a setup for it. So P will equal X over N, or another formulation of this is that X equals Pn. So we'll use both of those as needed throughout this section. I just want you to be comfortable with it. So in particular, if we have P1 equals X1 over N, 1, and P2 equals X2 over N2, and the two groups are independent, then we can make a combined proportion. And that looks like the following. All I do then is, as I did in that example, I'll call it P with a bar over it. So this is the combined proportion. And that'll be X1 plus X2 divided by N1 plus N2. So this item here is what we will use throughout this section. Let me fix my circle. It looks bad. Let's see if I can. So this will be what we use throughout. Now remember, with P, there's also a corresponding Q. If you'll recall that Q equals 1 minus P. So similar to this, I can do something like this with the P bar. So P bar equals X1 plus X2 over N1 plus N2. Now what I'm going to do is use the definition. Remember X, let me come back up for a second. This version right here, I want to use X is equal to Pn. So in particular, X1 will equal to P1 N1. Now, for a sample proportion, your book insists that we put that over top of it. So I will do the same. Similarly, I can do P2 N2 and divide by N1 plus N2. Now, P hat is no different than an ordinary P in that 1 minus Q hat will equal P hat. So let me go and write that in the next step. So I'll replace P1 with 1 minus Q1 hat times N1 plus 1 minus Q2 hat times n2 all over n1 plus n2. And now I'm going to distribute throughout the numerator. So if you look at this piece, if I distribute it to these two pieces, I'll get n1 minus n1 q1 hat plus n2 minus q2 hat n2. I guess it really doesn't matter where I put them. And that's all divided by n1 plus n2. Let me combine some terms. Well, not really combine, but let me gather together some things. I'll put the n1 plus n2 first. And then I'm going to subtract out, or I'm going to factor out a minus 1 from the other pieces. And that is a q1. Now, according to the rules of fractions, I can break this up into the following way. All right, for the first piece, I have the same number divided by, I have the same number in the numerator as in the denominator, so all of that is equal to 1. Over on the other side, those q's are in the same places where the p's are in the initial definition. If you look, the original overall proportion had n1 p1 and n2 p2 in the top. The overall Q, I don't know what else to call it, the not proportion, I don't know if that's even a good word to call it, the overall Q is the same definition. So anyways, instead of where you saw those P's, now you see those Q's. That's our definition of the overall Q. So we have, just like before, P bar equals 1 minus Q bar. So P bar will be the overall proportion of the two samples. Now for the standard deviation for proportions, it's given by the following. Usually what they'll write is sigma sub p hat, and that will equal the square root of pq divided by n. And my square root looks a little ridiculous. Let me fix that a little bit. Now, let me rewrite it in one more way, and you'll see how it relates to what we're doing here. So for one sample, this would be the standard deviation, or for one population, it just depends. This is our standard deviation. However, when you have a population, or you have two samples, we do the following. For this, we have two samples, and two sample proportions. So from that, with those sample proportions, we have two different n's. The standard deviation that we'll get is P1 hat minus P2 hat. And notice how it's similar to what we're doing here. We're going to have P bar, Q bar, remember those are combined, 1 over N1. That's where I would stop if this was just a one sample deal, but I have two samples, so I have to throw in the second sample size. The sample stat looks like the following. We'll be using the Z table for this. We'll have P1 hat minus P2 hat. Those are the sample proportions. Minus, these are the proposed population proportions because they come from two different populations. And this will all be over sigma P1 hat minus P2 hat. And let me go and write one more step because we'll typically be able to do this all in one step. I'm going to have P1 hat minus P2 hat minus P1 minus P2. Now this portion in parentheses will usually be 0. Not always, it depends on the problem, but it will usually be 0. And then I'll replace the sigma with what it equals. That's P bar times Q bar times 1 over N1 plus 1 over N2. So those are the things we'll be working with. Let me write down the hypothesis test steps. So this is the hypothesis test for two proportions. First, we have to verify that the samples are random and independent. Something we'll usually assume throughout all of these problems anyways. Part 2, we have to do just like before, where you have to show that NP is greater than or equal to 5 and NQ is greater than or equal to 5. Now we have to show it for all possibilities. N1P bar needs to be greater than or equal to 5. Then I need N1Q bar to be greater than or equal to 5. N2P bar is greater than or equal to 5. And then N2Q bar is greater than or equal to 5. So we have to verify all 4 of those things. Specify alpha. And then use the normal table. Then I think we need to compute the test statistics, so let's go ahead and do that. And that, of course, is Z equals P1 hat minus P2 hat minus P1 minus P2 all over the square root of P bar times Q bar times 1 over N1 plus 1 over N2. And then make the decision. Let's do some examples. All right, let's start with the first one. My claim is that the population proportion for the first population is greater than the population proportion for the second population. What are my sample stats? Let's see, I have S1, the standard deviation of the first sample is 6, N1 equals 20, S2 equals 4, and then N2 equals 30. And then test the claim at alpha equals 0.01. So first off, let's go ahead and put our null and alternative hypotheses. H0 and then HA. Well, since the inequality is strict, that's an HA. The claim actually goes into HA. Not only that, this is a right-tailed test. And then the other one, we changed the inequality, but we put an equals in there. P1 is less than or equal to P2. Now let's go ahead and get our critical value. So alpha will equal 0.01. Let's use the Z table. Or instead, I'm going to use the calculator to get this information instead of the table. And I'll show you how it works. So let's go ahead and grab our calculator. Now it's a right-tailed test, so keep in mind the tail is this little shaded region off to the right. That'll change things. Since I want the alpha being 0.01 means that the area of that little tail to the right is 0.01. Keep that in mind. Let's go ahead and go to second and then click on vars so that we can get to the distributions. Since I'm talking about finding a z value, I don't want CDF. I want inverse norm. That's number 3. So the area, don't put 0.01. You need to put 0.99. Otherwise, it'll give you something off to the left, which will be a negative number. You can leave mu equals 0 and sigma equals 1 because those are exactly the values we need for the standard normal table. And then enter your way out of this thing. And we get 2.326. So let me put that down there. Z naught equals INV norm. And the numbers that we put in were 0.99 because we wanted 0.99 to the left of the Z value. And then we put 0 and 1. And we got approximately 2.326. So let me draw a picture of this. Remember the way your calculator enters things here. 2.326. This shaded region here is a 0.01. That means over here is 0.99. The way the calculator works is it wants the area to the left of the given value. Now let's compute our test stat. So in this case, Z equals P1 hat minus P2 hat minus P1 minus P2 all over N1 plus N2. This equals my P1. I don't really have it. Let me come back here. You also did a mistake here, so let me fix that while I'm thinking of it. I used the letter S instead of X. These were the X's that I was talking about before. All right, so to get my sample proportions, I got to take X1 over N1. So let's get these things. So maybe I'll do it over here. P1 hat will equal X1 over N1. What is X1 and N1? That's 6 and 20. And that'll end up being 0.3. On the other hand, we have P2 hat. That'll equal X2 over N2. That there will be 4 over 30. And then, so P2 will be 0.13, and you could put a bar over the 3 because the 3's go on forever, or just stop after a few decimal places. It really doesn't matter to me. So for example, when I'm doing this, I'll put 0.3 minus 0.13. I'll put a bunch of 3's in my calculator, but as I mentioned, the parenthesis thing will probably be 0 most of the time. And then the test stat, which is totally bonkers. I don't know what I put that for. It looks like this: P bar Q bar times 1 over N1 plus 1 over N2. The P bar and Q bar have to be calculated. So the P bar will equal X1 plus X2 over N1 plus N2. So X1 we have 6 plus 4 over 20 plus 30, 10 over 50. That'll equal 0.2. It's best to work in decimals for this. So that Q bar will equal 1 minus P bar. That'll equal 1 minus 0.2, and that'll be 0.8. So when we do this, we'll have 0.2 times 0.8 times 1 over 20 plus 1 over 30. Calculate that whole thing. Let me go ahead and do it on the I think I'll do it on the calculator. Just to show you, start a parenthesis, put 0.3 minus, and then you can do 0.1. I know you can't put a 3 bar, but maybe I'll do a bunch of them just to be on the safe side. And you don't have to put -0. That really doesn't do anything, but I can put divide and then start doing my square root. So I'll have 0.2 times 0.8 times, now in parentheses, 1 divided by 20 plus 1 divided by, they do use that symbol here, divided by 30, and let's see what we end up with. 1.443. So I get approximately 1.44. Let's take a look at my shaded region. So if I look in there, I will find that it is out here, and we do not reject H naught. But stop. I didn't check something at the very beginning, and I should have. I didn't check these quantities. I didn't check all of these. So let me see. My N1 was equal to 20. So we have 20 times 0.2, and that equals 4. And that's less than 5. So it didn't even pass the very first step. So the test not valid. So it cannot use this test. Another example. Our claim is that P1 is less than P2, and our sample stats are the following. We have X1 equals 471, N1 equals 785, X2 equals 372, N2 equals 465. We want to test the claim at alpha equals 0.05. So I'm not going to be fooled like the last time. We need to make sure that all of the statistics work out. So actually, before I even draw the H naught and the HA, although I could probably do that first, but I don't want to. Let me do P bar first. P bar equals X1 plus X2 divided by N1 plus N2. And we have 471 plus 372 divided by 785 plus 465. And let's see, I don't think I won't do much of it on my own. I'll put parentheses around the numerator and denominator so that I could calculate these things. So there's my numerator, finish off the parenthesis and then divide, and then I'll have 785 plus 465. And then I can finish this off. Enter away. I get 0.6744, and that is actually exact. And then Q bar will equal 1 minus P bar. That'll be 1 minus 0.6744. So let me do that. So I'll do 1 minus, let's pull up the old answer. Enter. 3256. And now let me check all of my information. So N1 P bar, that will equal 785 times 0.6744. And 2 P bar was equal to 465 times 0.3256, and then N1 Q bar equals 785 times 0.3256, and then N2Q bar equals 465 times 0.3256. And let's get each of these numbers just to make sure they're greater than or equal to 5. So we start with 785 times 0.6744. And I have 529.404. So I'll just say that's approximately 529, but that's greater than or equal to 5, which is what I need. Let's move on to the next one. Here we're going to do 465 times 0.3256, and we end up with 151, approximately 151. That's greater than or equal to 5. Let's move on to the next. 785 times 0.3256, about 256, so approximately 256, which is greater than or equal to 5. You know, I don't care about exactitude at all. I just need a roundabout number just to make sure that these are big enough numbers. 0.3256. And that's approximately, I think I made a mistake here. This here, I did make a mistake. This incorrectly here. So let me fix this one up here. About 314. So that's greater than or equal to 5. So everything works out as far as the sizes that are concerned. So I may proceed with the test. So let me go ahead then and set up my H0 and HA. This time we had a less than. So we had P1 is less than P2. There's the claim. And that makes this a left-tailed test. So the null hypothesis that P1 is greater than or equal to P2. And let's go ahead and get our Z0 value. So we're going to use alpha equals 0.05. And then for the Z0, I'm going to use the calculator again, inverse norm. On this thing, you want to put the area. Since this is a left-tailed test and the alpha is 0.05, I'll actually want to put 0.05 and then the mean and the standard deviation for the standard table. So to do this, let me go ahead and grab my calculator for this. Second distribution, choose number 3 for inverse norm. This time put 0.05, you're talking about area to the left, and then enter your way through the rest of the problem. I get negative 1.645. If you use the table, that's the exact number you'll get as well. And so what we'll have is something that looks like this. And then we'll have this region in here, and that, of course, is the 0.05. Now let's calculate the test stat. Z equals P1 hat minus P2 hat minus P1 minus P2, that part will be 0, all over P bar, Q bar times 1 over N1 plus 1 over N2. Let me get all that information. P hat, P1 hat, I don't actually have it. I have to do, to get that, I'm going to have to do x1 over n1. So 471, so let me get these numbers. P1 hat equals 471 over 785. And let me see what that is approximately. So I get 0.6. I like when they work out that way. P2 hat would be 372 over 465. And I won't bother you with this computation. It's actually equal to 0.8. Let me put in my numbers then. So I have 0.6 minus 0.8 minus 0. We've already done P bar and Q bar. For P bar, I got 0.644 times, and then Q bar was 0.3256. N1 was equal to 785, and N2 was equal to 465. All of that is under the square root. Let me fix my 7 to make it look a little better. That still did not improve it. Let my calculator do the work here. So as usual, I'll put my 0.6 minus 0.8 in parentheses. The 0 that I'm subtracting in the numerator is of no importance. And I have the square root 0.6744 times 0.3256. You don't have to put times, but now I can start a parenthesis and do 1 divided by 785 plus 1 divided by 465. And end that parenthesis, and then just hit enter and it will give you the number. I get negative 7.29. There's our z value. Well, I think you can see that that is clearly way, way, way off in the rejection region. So we reject H0. For the p-value, and you have to be careful, there's a lot of p's going around here. For p-value, the p is actually capitalized. And if this time you're going to want an area, so you want the area to the left of a specific value, in particular to the left of negative 7.293. So I'm going to use a CDF for that. I want area is what I'm talking about. So here, p-value will equal, this time, let's see what I want the name is. Let me move this out of the way. Second distribution, it should be one of the CDFs. Number 2, normal CDF, and it has negative infinity, and then I'm going to put negative 7.293, and for the rest of it, you can leave those things alone since you're talking about the standard normal table. And my calculator is not able to give you it. It tells me, get this, let me write it down. Normal CDF, and what we did was negative infinity to negative 7.29301. And what it is the value is so small that your calculator cannot tell it from 0. I am going to use another calculator to compute this to tell you what it comes out to be. So the value that the calculator, I used another calculator and it gives me this. It gives me 1.53 times 10 to the negative 13. That means that if you wanted to write it out as a decimal, you would have 12 zeros. and then you would have 153. So you can see on one calculator, well, essentially that is 0. Well, 0 is going to be less than any alpha. P is less than alpha, which implies that we reject H naught. So we have a survey of 500 males, and then you had a survey of 500 females. So we've got our N1 and our N2. We've got our proportions too. The 15%, 0.8% were neither in school nor working for the males, and the 17.8% were neither in school or working for the females. So let's write these things down. They want to see, can you support the claim that the proportion of males aged 20 to 24 who were neither in school nor working is less than the proportion of females ages 24 who were doing the same? This is quite complicated. Well, let me write down a simple claim and see if we can follow what's going on from then. The proportion of males is less than the proportion of females. So instead of 1 and 2, I'm going to use M and F. Our sample stats look like this. We had, they didn't give us X1, but they gave us N1, or NM was 500, and then they gave us P1 hat was 15.8%. So these are for the males. Let me make that an M. So these are the numbers for the males. Then the females, we also had 500 of them, and the proportion of females in there was 17.8%. So test the claim. At alpha equals 0.05. Now, the fact that the samples are random and independent is always going to be said to you, but we still need to check for normality by doing NQ and NP. So we're going to do that first. Let me first calculate my P bar. Remember, that's X1 plus X2 over N1 plus N2. I know what N1 and N2 are. That's 500 and 500. I do not know what X1 and X2 are. To get that, X1 you can use, and I'm doing, see, this is typical for getting so used to a notation and not using what would be a more useful notation, and it would be much better if I had these labeled like this. So let's go ahead. XM, that'll equal NM times P hat M. So that's 500 times 0.158. That's 15.8%. This is 79. X sub F will equal N sub F P hat sub F. That'll be 500 times 0.178, and that equals 89. So I have 79 plus 89. That equals 0.168, and then Q bar equals 1 minus P bar. That equals 1 minus 0.168, which equals 0.832. Now let's check the inequalities. So I need to do NM times P bar. That'll be 500. P bar was 0.168. NM Q bar, that'll be 500 times 0.832. And F P bar will equal 500 times 0.168, and F Q bar That would be 500 times 0.832. Hopefully you see that you only got to try one of these things and the rest of them will fall out. So let me do the 500 times 0.168. I get 84, and that's greater than or equal to 5. I think you can tell the next one is greater than or equal to 5. It's going to be bigger than the first one I did. And I don't need to check the other two because, well, it's the same exact numbers that I just checked. So everything is greater than or equal to 5 as needed. Now let's go get our Z naught. Alpha, in this case, was equal to 0.05. We have a left-tailed test. So let me put my H naught and my HA. I probably should have done this before I specified my alpha, but HA was that PM was less than PF. So the probability or the proportion of males is less than the proportion of females. So H naught will be PM is greater than or equal to P sub F. We have ourselves, that's the claim, and that's a left-tailed test. So now this is when I need the alpha equals 0.05. My Z naught, since you're looking for a Z naught, you're going to use the inverse norm. And you want to specify the area to the left. Since this is a left-tailed test, you're going to be doing something like this. So you're going to want to specify that much area. The area to the left is that. And then I believe the rest of it is just going to be 0 and 1. Let's see if I remembered that correctly. They may have you. No, they won't. Let's see what happens. Let me turn it on. Go to my distributions. And I want to go to inverse norm. So number 3. And all they do want is the area, 0.05. And then enter your way through the rest of it. Negative 1.645 as we've seen before. And now let's do our test stat. And as always, I'm forgetting about my notation. I hope that by continually fixing this, you see that maybe it'll help you memorize it to always put these things down. And let's put all of our information in. I was actually given the p-hat values. I was given 15.8% for P sub M, so I'm going to change it to a decimal and write 0.158. The P sub F hat was given as 17.8%, so that's 0.178 minus 0 in the parentheses. My P bar was equal to 0.168. My Q bar was equal to 0.832. And then the sizes of these things were each 500. And let's go ahead and let our calculator do the work for us. So we get approximately negative 0.846, 0.846. Let's see, we have, when we look at that, that is over here somewhere. So we fail to reject H naught. For the p-value, this time you're looking for area, so you set p equal to normal CDF, and let's see what arguments are required for normal CDF. Second vars number 2. So I'll need a lower bound and an upper bound. So this is where you can use negative infinity up to negative 0.846. So let's get that in there. Negative 0.846. And then you can enter your way out of this thing. And I get 0.19, well, 0.2 to 3 decimal places. So remember, the things were negative infinity, negative 0.846, and then you could leave the rest alone. And then what it gives you here for approximately 0.19, well, let's just say 0.199, 0.199. Now alpha was 0.05. So hopefully from that you can see that P is greater than alpha, which means that we fail to reject H naught. All right, here we have a textbook example. We are looking at intermarriages, marriages which are between a husband and wife or spouses that are of different races or ethnicity. So what we have are samples of 1,000 Asian newlyweds, 1,000 Hispanic newlyweds, 1,000 black newlyweds, and 1,000 white newlyweds. Now what we want to do is take a look at the proportions of intermarriages there are between them. And most of the examples will do that. We're going to look at just one example, which are Hispanics and blacks. Let's start with the claim. Can you support the claim that the proportion of newlyweds Hispanics who have a spouse of a different race or ethnicity is different from the proportion of newlywed blacks who have a spouse of a different race or ethnicity? So let's take a look at what a claim like that might look like. Let's do the claim is the word different here. So we want to know if the proportion for Hispanics is not equal to the proportion for blacks, something like that. Our test stats look like the following. We have the number of Hispanics was 1,000. Well, all these sample sizes were 1,000, which is always nice. And then the sample proportion for Hispanics is given in the picture. We can see that that's 27%. And the proportion for blacks is also, the sample proportion is given in the graphic, and that's 18%. So we want to test the claim at alpha equals 0.05. And as usual, you want to calculate P hat and Q hat. And you want to do that first because you really can't do anything until you've calculated these things. So let me go ahead and get my P bar. That'll equal, well, one version is like this. Now, while I know those n's below, they're each 1,000. I would actually have to calculate those things above, or you could use the formula. So I could use pH bar times NH plus PB bar times NB. And this will do it all in one shot. So let me get those informations. 27% was pH hat, so I'm going to convert that to a decimal and write it as 0.27, and 1000 was equal to NH, plus, and then PB hat was 18%, so that's 0.18, also times 1000, and the denominator is 2000. You can do most of this without your calculator, I think. The 0.27 times 1000 is 270, plus 180 over 2000. That's 450 over 2000, which equals 0.225. And then Q bar will equal 1 minus P bar will equal 1 minus 0.225. That'll equal 0.775. And then when you do all your computations, if I go NH times P bar, that'll be 1000. P bar was 0.225. Well, that's 225, so that's automatically greater than or equal to 5. NHQ hat, that'll be 1000 times 0.775. Well, that's 775, so that's greater than or equal to 5. When I do the other two, NB P bar, that will exactly be the same as the first computation. That'll equal 225, that's greater than or equal to 5. And then the NB Q bar will be 775, and that's greater than or equal to 5. So all that's taken care of. Now let me write down the null and alternative hypotheses. The alternative hypothesis was the one that is not equal. So pH does not equal PB. There's the claim. And notice that this is a two-tailed test. And then the H naught would be pH equals PB. Now, did I already start the solution to this? Yes, I did. All right, so there we have those things. Let's go ahead and do our alpha that was given to us was 0.05. So alpha over 2 equals 0.05 over 2, which equals 0.025. And remember, this is if you're going to draw a picture of the situation. It's going to look like this. You're going to have little pieces at the end. That'll be 0.025. Then you'll have this 0.025. It's important because the calculator may ask you for something. We have a Z naught, and remember this Z naught will be the negative of whatever the other one was. So you'll have two Z naughts, but one will be positive and one will be negative. Let's see what the calculator does for us. I think what I can do, since I want a Z naught, I'm going to do an inverse norm of 0.025. So let's go on. Second, distribute. Since I want a Z value, I want to use inverse norm, so I want number 3. So the area, I'm going to specify this 0.025. And then I'll go ahead and enter my way out of there. I get negative 1.906 to 2 decimal places. So let me write that down. Z naught and all we did was put the area 0.025 comma 01, and this gives you the left value. We get approximately negative 1.96. Now you can also just make it positive for the other Z naught, or for the other one you can do inverse norm. This time you'll have to specify 1 minus 0.025, and you can actually write that in the calculator. It'll actually do that. And it will give you approximately 1.96. So those are my critical region beginnings, and let's go ahead and calculate our test statistic. Here we're going to use z equals p. I want to make sure that I use my letters this time. ph hat minus pb hat minus ph minus pb all over p bar q bar times 1 over n1 plus 1 over n2. Now let's put our numbers in. pH hat, what was that? That was 27%, so that's 0.27. PB was 18%, so that's 0.18 minus 0. My P hat was 0.225, or P bar, I'm sorry, 225 times 0.775 times 1 over 1,000 plus 1 over 1,000. This comes out to be approximately 4.819. Let's take a look in the, that's quite a bit in the critical region. Let me draw my little critical regions again. One of them started at 1.96, and so that is most definitely in there. So we reject H naught. For the p-values, this time you want an area. So, and it's split into two pieces. So what we can do for our p-value is we can do p equals 2 times, and this time since I want an area, I'm going to use normal CDF, and what information will I need to have in there? Let's go ahead and grab it. So that is number 2. And so we could, actually though, I would like to know the area to the right of 4.819. So I'm going to start it at 4.819. And then I am going to go to positive infinity. Remember how to write the positive infinity in this calculator. Enter your way out of it, and we see a very small number. So let me write down what I had. 4.819, then we went to infinity, and then 0, 1. And so that's approximately 2 times, let me see what that number was again. 7.223 times 10 to the negative 7. Now to get your calculator to do that, all you got to do is say times 2. So now I get 1.445 times 10 to the negative 6. And of course that means you move the decimal to the left 6 places. So this is 0. There'll be 5 zeros before you have 1445. And the alpha was, the original alpha was 0.05. So I think we can see that P is quite a bit less than alpha, which means that we reject H naught.